Thank you very much for the introduction. There has to be some kind of award or reverse award for the last paper in the program. Thank you for sticking around. So this is joint work. This is Huda's work. She couldn't make it. Like it sounds like a lot of people, because she couldn't. If she came here, she couldn't come back to the U.S. As well as Ziyun Kian and Ajaya Nupani. GPUs are everywhere. I mean, they're on your phones, on your desktops, on the cloud, and they happen to run a lot of important workloads. So when you think about graphics, they're rendering what you're seeing on the screen. When you go to the cloud, then there's a lot of sensitive data that runs on GPUs. And so I'm going to tell you, I'm a computer architect, so this is kind of a pleasure to talk to a security community. I do computer security and architecture, but I'm going to tell you a little bit about GPU architecture, explain a little bit. So we've seen a lot of side channels on CPUs. Why? Not surprisingly, the problem is going to manifest on GPUs. And then I'm going to walk you through a series of 3 attacks. There are graphic stacks that you can use to program the GPU, but there are also computational stacks. And it turns out that you could do attacks kind of in a different set of vectors from one to the other. And then I'm going to talk a little bit about mitigations. So I hope this doesn't scare you. But GPU is massively parallel. There's a lot of, it's throughput bound. It does a lot of processing that is similar at the same time. If you look in there, the word SM, you want to think about it roughly as a kind of a processor. So it's a multiprocessor. But within every SM, it's running this, what is called as SIMT model. So you issue instructions that operate on 32 values at a time, right? So you schedule instructions from different, what we call warps, which are groups of threads. And then every instruction basically just issues the same operation on 32 values. Different processors. So 32 is the most common. You could have, there are kind of wider and narrower processors, GPUs. There are caches. They tend to be smaller. And at the same time, they have a lot of pressure on them because you have this, a lot of threads operating at the same time. There are L1 caches in the SMs, but there is also an L2 cache that is shared across the whole GPU typically. So I'm going to tell you a little bit about the programming model so that at least just we have some vocabulary to talk about. So on the computational side, the programming language is CUDA from NVIDIA, or OpenGL, which is supposed to generalize to a whole lot of different accelerators, so GPUs and others. So you program using these kernels, and the kernels can be like a bunch of threads. Let's say each thread is operating in a pixel in an image. And then they get scheduled by 2 hardware schedulers to eventually run on the GPU. One picks which SM it's running on, and then once it goes to the SM, there's another scheduler that picks instructions from the ready warps. So let's say a thread experiences a cache miss, and then we have to wait for a long time. We have a bunch of other warps that are ready to schedule from. So it's throughput bound. It's focused on pushing a lot of operations through rather than being latency bound like CPUs. At the same time, they're programmed from the graphics side, and there's a graphics pipeline that honestly I'm not an expert on, but the areas that are in blue, the way that GPUs became programmable is now we allow those shader parts to be programmed. So then if I'm thinking about writing an attack code that I'm going to embed in, let's say, OpenGL, then those boxes I can replace with my own code. Okay, but then there are also still kind of non-specialized pieces of hardware that are just basically the graphics run through them and they operate on them. So you take your input, and then you build the triangles, and then you add the texture to the triangles before dumping everything in the frame buffer to display the image. And this is sort of, if you want to program here, you're using something like OpenGL or WebGL, which is sort of a web-based interface that allows you to do similar things. All right, so the GPUs are getting wider. They're getting much, much more massive every generation. And as a result, the cloud providers are interested in sharing them. So there's a push to share them. They've always been shareable, but kind of in a clumsy way. as we go from Pascal, where the sharing was essentially software, you run everything through one process, and then the process pretends as if it has these concurrent programs, to the point where we have hardware now to support separate address spaces in the same GPU. So it's clear to see that we're going to get to the point where sharing is the norm on the cloud, right? Especially as they get wider, you want to get your money's worth, so you're going to be issuing multiple workloads to the GPU at the same time. All right, so we hear sharing, then we think possibly side channels. So we had a paper last year in Micro where we investigated the presence of covert channels. So I have all of the shared resources. Can I actually use it to communicate when I'm collaborating? And it, not surprisingly, this is the case. We had to solve some problems, reverse engineer those hardware schedulers to put them together, then build channels, and then remove the noise. And that also actually uses the hardware scheduler to make sure nobody else can run. And it turns out that this is sort of older generation GPUs that you can get, because of the massive parallelism, you can get, awesome covert channels, 4 megabits per second. I think we've done this on the Volta this year, and you're in the tens of megabits per second, sort of eventually kind of limited by cache ports and things like that, not by, the lack of things to beat up on to communicate ones and zeros. So from there, of course, covert channels are easy. They tell you that there is some timing phenomena. I should say that there's a couple of other papers. One looks at power side channels, and another one looks at a CPU process sending something to the GPU and then correlating the timing to some secret, right? But nothing that uses two different processes, one spying on the other. So we started out thinking, well, can we do the obvious stuff? Can we take prime and probe or standard CPU techniques and apply them to the GPU? And it turns out that probably the answer is not. I'm not ready to say completely that that's not the case, but essentially, collocation is different. But the main issue is that the caches are really much smaller, and they're getting beaten up on by a lot of different threads. So you see signal, but you don't know where it's coming from, and there's not a lot of information that you can get. When you think about control flow-based attacks, so if you want to look on the iCache and see if you jump to this piece of code or this other piece of code, well, this SIMT model, if you have branch divergence, you're going to execute this part and then that part. So you see the same signal no matter where the threads went. So it's kind of a different approach. So we ended up kind of changing tactic. And I'll tell you a little bit about the leakage sources that we looked at. So our threat model is we have a process that is running on the same machine. It doesn't have any special privileges other than it's allowed to use the GPU. And then we look at, we consider a victim that is a graphics workload, and we consider a victim that is a computational workload, and sort of the opposite for both of these cases, whether the attacker is coming as a graphics process or the attacker is coming as a computational process. So that's sort of this kind of weird looking matrix there. And our key challenges are understanding how this collocation happens. So how can I get the bad guy and the good guy together, and what is visible at that point? That's the second part. What leakage can we get? And we wanted this aggregate leakage because the fine grain leakage, as I told you, is not very precise here. So it turns out that there are sort of leakage APIs that are fairly easy. So there's a memory allocation API. So if you want to run on the GPU and you want to know how much memory is there, you can ask. And it tells you. And of course, what's not available is being used by the victim. It turns out that there are great performance counters on the GPU. And whereas, for example, x86 allows you to get 4 values from your performance counters, we can get 200 and something values for GPU performance counters. So a lot of signal that we can tap into. And of course, we can always do timing. So we can sort of figure out how much our own code is running for, or how much somebody else's code is running for. All right, so the first scenario is there's a graphics workload, browser running, and I want to figure out what it's doing. I want to extract some information about what is happening inside of my browser. So the attacker is an OpenGL, and then the victim is a browser running WebGL or some other application running OpenGL or something like that. So the first step is establishing this collocation. So we wanted to see if there are two graphics workload, what happens to them? Do they run on the GPU at the same time or not? And this is a little bit about the reverse engineering. I will only say it for this case and then not bore you with it later. So we get both of these codes to run, extract information about where they are running. So you can get hardware information, which SM you're running on, what is your thread number, what is your warp ID. But the problem is there's no way to output these values back. So we had to encode them in the pixels of the image that we drew. So we kind of encode the output in the image, dump it back, and then read the values of the pixels, and from them figure out what are the internal parameters of where we're running and what SM we're running on. Okay, so we get this information, and then we figured out that essentially the hardware schedulers are round robin, and if you have resources, it will just kind of put you on the SM one by one until it runs out of resources. So we can co-locate as long as there are enough resources. Okay, so our first attack is website fingerprinting. It's kind of boring and kind of standard attack, but it was the first easy target. So in this case, we run the spy, and it measures either the memory API or the performance counters. So it's running at the same time. And for the memory API, actually, we don't need to be running on the GPU. It's sort of you can read it from the driver. You have to establish a context. You have to say you're interested, but then after that, you can read it. And then you get a time series signal of the memory allocations, the remaining memory on the GPU, which tells you, so that the memory that's not available tells you how much the victim is using. So over time, you see that you see things like this as a user browses a particular website. You see a time series signal that says, here are the allocations that are coming as they open a page. You're rendering a lot of objects. Each of them gets rendered separately on its own rendering operation, and you see sort of time series signals. We tried kind of standard time series classification approaches like dynamic time warping, but eventually what we ended up doing is segmenting into 4 separate areas, and then doing things like average, memory allocation, variance, kurtosis, things like that, and taking that as a feature, throwing it at some machine learning classifiers. The details are in the paper, and we get precision like something like 90% on the 200 top Alexa websites. Okay, so having done that, we extended the attack to say, okay, once I figured out that you're on Facebook, I can actually track your activity on Facebook by the same way, by having these time series signals as you open different pages until I get to the point where I figure out that you are typing in your password. And here I can actually use the timing of the allocation operations to capture your keystroke timing. So as I measure the time series, I see at what point in time the allocation happens, and that gives me just a clear signal of keystroke timing. So when the signal is flat, this is the refresh rate of the screen. And then when you see a dip in the time between the 2 allocation operations, that is basically an event happened and it's being rendered on the screen. So you see these little dips over here, tells you this is a 6 key password. And then we can use timing analysis to try to figure out what the key is. This is the distribution of the error, so measuring the actual time stroke value from the kernel or the graphics library. I forgot how we did it. And comparing it to the signal we got from the side channel. And again, a particular experiment you see with the error, it's very precise. You can get kind of very good keystroke timings. So there's the Keyed-Round paper from NDSS. It seems to not be working with browsers. We're still kind of working on that. But if it's true that this is not prevented by things like Keyed-Round, so this is another kind of way that this attack is dangerous. Okay, so another attack is the attack on CUDA. So this is more like the cloud environment. And I happen to start an Amazon AWS instance that shares GPUs. Currently, we don't think that the sharing is done. So MPS is supported, but NVIDIA literature says among mutually trusting processes. But assuming that you can get them to share, and we really think that this is coming soon, then you can measure again. So now the sharing that I mentioned goes through something called the MPS process. I'm sorry, not MPI service process, MPS service process. And it multiplexes the 2 kernels as if they're coming from the same process and then sends them to the GPU. Some GPU virtualization proposals do something similar to virtualize the GPU. But as I mentioned, kind of GPUs on the market now have support for hardware address spaces. So they're intended to start sharing soon if they're not sharing already. And in this case, we monitor GPU performance counters. Now, a limitation of the GPU performance counters on CUDA is that you can only get them when a kernel finishes execution. So we launch a bunch of kernels right after each other, and whenever one of them ends, we get, so they're very short, whenever one of them ends, we get a sample of the performance counters. So we wanted to do something like a model extraction. This is not a deep neural network application. It's from the Rodinia benchmark, which is used to evaluate GPU performance. It's a regular neural network, and we wanted to see if we can use the side channel to get the parameters of the neural network. It's configurable. You can put whatever neural network that you want. So this model extraction attack, these neural networks are secret a lot of the time, and if you're able to get the hyperparameters, then this is an important advantage for an attacker. So the SPY launches several hundred CUDA kernels. Each of them gives you a sample of the performance counters. We reverse engineered the collocation, but it's not really important to us now. So just to make sure that they do happen on the same, we can put the kernels on the same SMs. What we use our kernels for is to generate a lot of contention on a lot of resources, because, for example, let me say I flush the cache, then we can see the victim's behavior as it accesses the cache, and we get a stronger signal in terms of the performance counters. The machine learning details are also in the paper. Essentially, we took the 250 some performance counters. We did information maximization to extract the most informative features. There were like 22, and then we took the time series values of those and the same thing, segmented them, and took the mean, standard deviation, kurtosis, those things, and then threw it at different machine learning algorithms. And we can recover the precise neural network configuration with that performance over there 88% of the time. So kind of a dangerous source of leakage if, you know, multiple applications are running on the same GPU on the cloud. Okay, so we did also a CUDA graphics side channel, similar results, very high accuracy on website classification. So as far as mitigation is sort of kind of less interesting, I think. We focused on similar resource API channels, and the idea there is you reduce the precision that the attacker has. So we either limit the rate of how often you can get these values, or we limit the precision of these values. And you can see the kind of what happens to the precision of, I believe this is the website fingerprinting attack. So if you limit the rate of the calls, if you limit the precision of the calls in kilobytes for the memory API, and then if you combine the two, you see kind of a qualitative strong drop in how good the channel is. Okay, so basically that's all I had. We had fun with some side channels on GPUs between two concurrent applications. I believe this is the first paper that demonstrates that this is possible. We looked at some mitigations, and now we're looking at things like DGX2, which is the new NVIDIA sort of big machine that has multiple GPUs. The plan is to introduce cache coherence between them. The current toy that we have doesn't have cache coherence, so that introduces a lot of opportunities for kind of data-dependent, measurable behavior side channels, in other words. We're also looking at integrated GPU systems, so what's on phones. All of our experiments are, I didn't say, are on a discrete GPU, so that this way the memory API makes sense. I think the performance counter API makes sense. We just have to figure out under what threat model we're able to measure it on Android or kind of mobile operating systems. Thank you, and happy to take any questions.
Thanks a lot. This is a very interesting talk. So okay. So you know me. So I'm Kanguk Ji from the NS Labs. Okay. Actually, I'm typically interested in attacking the like a machine learning algorithm.
Okay.
So actually, it was very interesting, but the accuracy was a little bit low. So can you tell me more about what was actually workload or model, and then what was actually you were trying to? So
it's so we are not machine learning experts, and this was just sort of a proof of concept. But the Rodinia benchmark, which is kind of a benchmark that computer architects use to evaluate GPUs, has a benchmark on neural networks. If you are interested, I can send you the link to the actual code. Okay. And we were looking for the precise number of neurons in the model. So accuracy is low, but we have like a large range, and we're able to pinpoint the number of neurons that they use.
Yeah, actually, because there are some standard data set
Yes.
and then models that the people talk.
We should talk. I'd be happy to try to see if we can get any information from those.
Okay, great, thank you.
Thank you.
Okay, so from John Hoskins, I like your work, very solid. So I'm interested in the website fingerprinting attack. So I wonder if the patterns you observe, like I remember the graph has 3 figures about like a Facebook and Amazon, that one. So the pattern changes if the browser adopt different rendering techniques. For example, anti-aliasing is enabled or disabled, or like use like software rendering, or use different GPU like integrated or NVIDIA. So that pattern change.
Yeah, that's a great question. So we looked at some of these factors, including sort of differences in the size of the screen. And it turns out that it makes a difference. I mean, there is still kind of quite a big signal across a different set of variations. But if you can identify the configuration, then I would sort of stage the attack to try to identify the configuration of your browser and then start sort of doing more precise classification. Yeah,
thank you.
Thank you.
Ardal and Amir Sani, UC Irvine, very nice work.
Thank you.
So some GPUs have virtualization support. I was wondering if you've looked into whether they mitigate any of the side channels, or, for example, Intel GPUs, the integrated ones,
Yeah, we have not looked at that. So GPU virtualization is definitely on our radar. I know you do some work in that area. If you're interested, we can try to see if.
Sure.
Yeah. Thank you.
Fengwei Zhang from Wayne State University. So for the side channel, I believe you leverage the performance counters on the GPUs. You also mentioned, if I understand correctly, it seems that you require the kernel privilege in order to retrieve the data from the performance counters.
No kernel privileges. So everything that we run is user mode attack. So yeah.
Okay, cool. Thank you.
Yeah, thank you. So I should say we reported all of this to NVIDIA, AMD, and Intel. And NVIDIA's fix is to try to make performance counters configurable by the administrator to be kernel mode only, but still they haven't come out with their public disclosure.
All right. Let's thank the speaker.
Right.